May I ask?
So good morning, everyone. This is the 10th lecture. So let me get this slightly higher up. This is slightly better. Okay.
Sir, will there be a quiz?
This is lecture 10, and so last time we showed the following, that last time
Sir?
we showed that the only one parameter groups of diffeomorphisms of linear transformations on Rn or or of the form e to the Ta, where let me say Gt equal to e to the Ta, Gt equal to e to the power Ta, where A is an n cross n matrix, is the phase velocity generated, i.e. Gives the phase field x going to Ax. So at any point in Rn, you have this, at any point x in Rn, you have this new vector Ax attached to it. It's like the velocity vector. It is a velocity vector at x. It's in a different direction from x, but depends upon x. Depends upon x in a linear way. And you know, find integral curves of this vector field, and they have to be of this form. That was the content of what we showed, and this is precisely the solution of homogeneous linear equations of the form x dot is equal to Ax. So all of them will look like this. So now we need to get into a little bit of algebra. We can't help it. So to understand the solutions better, is the light at the back bothering you? Okay.
No.
If not, then fine. Okay.
Sir, shouldn't it be lecture 11? Oh.
So now we will talk about, I don't know how much of the forms you know. So I'm going to just remind you very quickly. What Professor Purushottam Rath told me is that last year, at the very last lecture of the semester, he told you about Jordan canonical forms, but did not prove anything. So I'm just going to remind you what the Jordan canonical form is. So okay. So a Jordan block matrix is a matrix, is a square matrix of the form J is equal to, on the diagonals it's all lambda, and on the off diagonal terms it's 1. Not all the off diagonal terms, it's what's often called the super diagonal. Okay, so this is where it is 1, and this is sometimes called the super diagonal, and 0 elsewhere. Okay. Um, sometimes called the super diagonal. And the line below it is often called the subdiagonal. So if you want to be more precise about what to call these things, you can actually put in all kinds of decorations. If it's n cross n, then you say jn, lambda, etc. Okay, you can put decorations. To indicate what are the other things it depends upon. So this may not be so clear what to do. So the main theorem involving Jordan canonical forms on algebraically closed fields. So this is, it's clear. Two remarks. Okay. One, lambda is an eigenvalue of j lambda. Okay. And E1 is the only eigenvector of j lambda. And obviously, this eigenvector has to have eigenvalue lambda because lambda is, this is generally true. So all this works over an arbitrary field, the arbitrary algebraically closed field. But this part, whether algebraically closed or not, if this Jordan canonical form exists in this form, if there is such a J, what I'm saying is true. Okay. Two, over an algebraically closed field, one can and a finite dimensional vector space and a linear or algebraically closed field, any linear transformation T from V to V on a finite dimensional vector space. Has a basis every. Let me say any. For any. We can find a basis of V such that the matrix of T with respect to V1 through Vn looks as follows. Okay, so the way it will get drawn, I'll have to use the next page. So then the matrix of T will look like J1, J2, JK, 0, 0. The matrix A of T.
Sir, can you scroll a bit above?
Where,
sir, can you scroll a bit above?
the above display
Can you
is
hear it?
in a
Can you
block matrix form. And the matrices J sub I going from 1 to K, are all Jordan forms. Okay. Are all block matrices, are all Jordan block matrices. Hi, Arka, you had a question?
What?
Sir.
Yeah, I can't hear you guys, that's true. So I don't know why I'm not able to hear you. Send a message if you can. Somebody say something.
Sir, am I audible?
Yes, Arka, you're audible.
Okay, sir.
Okay, yeah. Okay.
Sir, also the screen sharing got turned off, I guess.
Just now or later, earlier?
So like when the call came.
Ah. Okay. So this devices are all connected to each other. So that's the problem. Okay.
Sir, can you scroll up a bit?
Can I what?
Scroll up.
Scroll up. Okay, here we go. So let me say what I was trying to say. I'm going to start from here, Krishnan. So I hope that works. So the lambda is an eigenvalue of j lambda, and EI is the only eigenvector of j lambda. Okay, for Jordan forms of this form. Okay. If you have a Jordan form like this, or Jordan block matrix like this, then it looks like this. Over an algebraically closed field for any Jordan canonical form, it must, you can break it up into, your T can be broken up in, you can find a basis so that the matrix of T, which you'll call A, can be decomposed in the following manner. Okay, where each of these are Jordan blocks. Okay, with perhaps the same eigenvalue. We are not saying all different eigenvalues or all Jordan block matrices. 3. The number of Jordan blocks corresponding to an eigenvalue lambda. So it's quite possible, say you have an eigenvalue lambda, it's quite possible that this one, that one, and somewhere in the middle are Jordan blocks with that eigenvalue. But of course, if you have any reasonable clerical skills, you will put all the Jordan blocks with the same eigenvalue in one set with another one in another set, and so on and so forth. Is the geometric multiplicity of lambda. Okay, by this, does anyone know what geometric multiplicity means? Or is anyone who doesn't know what geometric multiplicity of eigenvalue means? It's just a dimension of the corresponding eigenspace. Okay, and the matrix is diagonalizable if and only if the geometric multiplicities of each of the eigenvalues is equal to the algebraic multiplicity of these eigenvalues. Okay, that's all easy to see. For the Jordan form above for T is canonical in the sense that up to permutation of the blocks, any two Jordan forms for T are the same. Even if you choose a different, it's quite possible another set of bases also breaks up. So this is pretty much canonical. I'm not saying that the basis is canonical. Okay? I'm not even saying that any two bases would be permutations of each other. For example, if you have a scalar matrix, I mean a matrix which is just lambda times the identity, then every block looks like just 1 cross 1 matrix, lambda, 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 lambda. Okay, but there's enormous choice for what basis to pick to break this up into Jordan canonical form. In fact, take any basis that you wish. If in one basis your matrix looks like lambda times identity, in every other basis it looks like lambda times identity. So there's nothing God-given about this. Okay? There could be more than one set of bases which break up your linear transformation, the matrix of that, into a Jordan form. Be that as it may, two different ones will give you more or less the same same Jordan canonical form. Up to what? Maybe you will permute these things. Maybe this becomes a second block, this becomes a fifth block, and that becomes something else, becomes the first block. Up to that, up to permutations of the blocks, any two things look the same. Okay? So that's really canonical. It is a signature of your linear transformation, your Jordan canonical form. Okay? So that's what, and the proof is not very hard actually. I won't be proving it, but the proof, there are many proofs. There are many proofs of this. The standard one nowadays is consider the PID Kx, where x is a variable, is by variable I mean it does not satisfy any algebraic equation. It's a transcendental. Okay, and K algebraically closed. Okay, so look at any such field and look at the associated to the field is the principal ideal domain Kx, because it's a Euclidean domain. It's a principal ideal domain. Okay. Let T from V to V be as above. Then V is a Kx module via a polynomial via the formula take a polynomial and multiply it to a vector V is defined to be okay. That makes it into a module. It's a structure theorem of PIDs, which you will either have learned or will learn very soon. It's one of the first things you learn about modules over principal ideal domains. Every module, every finitely generated module M over a PID R looks like a direct sum of cyclic modules. So okay. So this is my notation for the principal ideal generated by R sub I. Everything looks like this. So apply this to the case R equal to Kx and M equal to V, and you'll be done. Okay. Then V looks like that some I going from 1 to m, or mod I'm using the fact that it's algebraically closed. So any ideal can be broken up as linear factors, and then use the Chinese remainder theorem that the factors which correspond to one particular thing will look in a certain way. So anyway, it comes down to this. Okay? So this is how okay, one checks that this gives the decomposition of T. I'm not going to go into more details because all this will be done with in great detail in some point. At some point in our syllabus, we used to have Jordan canonical forms in the first year, but it in linear algebra, but it did not make sense because its applications would come much later. Okay, and people would not remember it, so it's better to have it later. Unfortunately, in between Professor Shiva and I, the differential equations course changed, actually due to Professor Shiva. He does it in this theoretical way that I am doing it too. I follow Professor Shiva, who's retired, who had a certain view of differential equations, which is Arnold's view, and I'm following exactly that. So once that happened, one had to, so now one needs Jordan canonical forms sooner than we thought. So it's okay, so long as you know what it is. Okay, so that's the Jordan canonical form for anything. But we are not working on an algebraically closed field. So I want to talk a little bit about the real Jordan canonical forms. Okay, why are we doing this? Is for a good reason, because I know that solutions of linear differential equations with constant coefficients, I mean, of the form x dot equals ax, where a is a constant matrix, they are of the form, solutions are of the form e to the power ta. So now the idea is to break up e to the power ta, e to a into its Jordan forms, and then the exponential will just break up into block forms, each one of which is the exponential of the Jordan form. And to understand the result that we have been using without proof in the cookbook recipes for homogeneous linear differential equations with constant coefficients. We just said, look, here is a set of solutions. Okay. And the numbers match and they're linearly independent and you can check their solutions. So that's it. But now we're trying to give a theoretical justification for understanding how those solutions come about. I already know that that linear differential equation of order n is a scalar one, is really a first order linear differential equation but a vector valued one. Okay, n dimensional. The nth order becomes first order, but the scalar becomes a vector differential equation. So it's of the form, and if it's homogeneous, and that's what I'm going to talk about, because for the non-homogeneous part, we know variation of parameters works. We have to understand how to get the complementary solution. So in this case, we are looking at x dot equals ax, where a is a constant matrix. And so now I'm going to understand that further, because I know from experience with the scalar thing, and because of the way the chief chefs in the kitchen have taught us how to cook those things, the recipe they've given, I know that the ingredients are exponentials. Well, cosines and sines are also exponentials. That's it. So and now I'm trying to understand how they came about, and that is what the next two lectures are about. And that takes us into Jordan forms. And let me understand real Jordan forms. Okay. Okay. So, so they're often just called real canonical forms. So interesting real Jordan canonical forms. So let T be an endomorphism of R. Let me remind you that this is the same as that. So let T be a linear transformation from Rn to Rn, and A belonging to MnR. It's matrix with respect to the standard basis on Rn. Okay. So regarding A as a complex matrix, okay, we have a we can and as in ANA2, okay, then as in ANA2, A is the matrix of the complexification of TC from Cn to Cn, with respect to the standard basis in Cn. Okay. For those who are in backlog and weren't in ANA2, this is not so crucial. I'm just looking, so very quickly, A is a matrix of real numbers. I can think of it as a matrix of complex numbers. Okay, why not? So it gives a linear transformation from Cn to Cn. Basically, in short form, that's all I'm saying. Okay, and for those, and this also works for those who do not remember our the bits we did about this in ANA2. Okay? It's not a big deal. This is how we have to think about it. Okay. From the description of the Jordan canonical form above, well, we can find a basis B of Cn such that T looks like star. Should we call it star? Okay. Such that the maybe I shouldn't have called this A. Okay, let me not call it A yet. So let's rewrite this. Sorry, I don't like what I've written. And TC from Cn to Cn, it's complexification. Then from the comments made above, we can find a basis B of Cn such that ordered basis, okay, such that the matrix of Tc with respect to B is of the form J1, J2, Jn where each block has the form okay. So therefore the Jordan decomposition.
Sir, will you please scroll up a bit?
Yeah.
Thank you. Sir, isn't the last one supposed to be directly above the lambda?
Yeah, it's supposed to be above the lambda. It didn't come out properly, did it? Yeah, it's above the lambda.
Yes, thank you.
It's on the super diagonal.
Thank
Okay. Therefore, the Jordan decomposition decomposes Cn into a direct sum Cn equal to V1 direct sum Vt. Okay, let's say there are T Jordan canonical forms. How many did I say? Let me call it Jt, J sub T. Okay, J sub T. Okay. Note J sub K can be regarded as a linear operator on V sub K. Okay. Whatever be K between 1 and T. That's what breaking up into block diagonals means, and breaking up the vector space in a compatible way. Okay. In this. So
Sir,
Sir,
you can just remind what like what properties this V1 to V2 will satisfy in terms of J, in terms of the Jordan.
So Vi, so if you have a block form like this, so there is a basis corresponding to the block form, and the basis vectors say, so obviously it means that J1 keeps some of these basis vectors together, say the first 5, and then you take the first 5 and take the vector space spanned by those first 5 basis vectors, and J1 will keep that invariant and will be 0 on the other ones, and so on and so forth, right? So, so this is just the way it works, is that if you look at
Do you mean that these are invariant subspaces?
of course, these are invariant subspaces. Okay.
Sir, will these be the eigenspaces of the corresponding lambdas of the Jordan blocks?
Will they be? Think about it. Let me remind you of this comment here. The eigenspace corresponding to this matrix is only one, this column vector. There is no other eigenvector. So these
Okay.
VIs are not eigenspaces. But each VI contains a one-dimensional eigenspace. The Jordan thing is a failure of diagonalizability. If you have a Jordan block of in your decomposition of dimension bigger than, or of size bigger than 1, that's a way of saying it's not diagonalizable. This is the next best thing you can do, but it's a way of saying this is not diagonalizable. You can go blue in your face, but it will not be diagonalizable because it has only one eigenvector, provided n is bigger than 2. N is greater than or equal to 2. If that is so, then there's only one eigenvector, namely that. The rest of them, whatever you do, you'll not get another eigenvector. Okay? So each Jordan block contains one eigenvector. It's quite possible that you have 3 or 4 Jordan blocks corresponding to the same eigenvalue. So suppose you have 5 Jordan blocks corresponding to an eigenvalue, call it, let's say the eigenvalue is 32. Then 32 occurs with geometric multiplicity 5. It occurs with a much bigger algebraic multiplicity, okay? Namely the sum of the sizes of each of these 5 matrices. Okay? So this is how it works.
Sir, why the algebraic multiplicity is the sum of the sizes?
Why I don't want to do a whole theory of Jordan canonical forms, but the sum of the sizes of the things will be the algebraic multiplicity. That's not hard to see, actually.
Sir, can this be covered in a tutorial, the theory behind Jordan blocks?
No, I don't want to. This is an algebra thing. Okay, we should know how to use it. Okay, I mean, I don't want to waste the tutor's times on something like this. I'll give you a reading material if you want to read. Okay. Anything else?
Yeah.
Okay, I can tell you how this works actually. There's something called a minimal polynomial. Take the characteristic polynomial, take what's called the minimal polynomial associated with it. Then you look at the breakup of the minimal polynomial. So you'll be able to find spaces which are called generalized eigenspaces. The VIs are not eigenspaces, they're generalized eigenspaces. They are the spaces on which T minus lambda, so for J1, say J1 has lambda 1 associated with it. So it will turn out that there'll be a point where t minus lambda 1 to the powers something becomes 0. And on a particular space. So then you look at the kernel of t minus lambda, that'll be, or t minus lambda to that. Okay, so it has to do with the fact that on these spaces, it's not t minus lambda that is 0, but t minus lambda to a certain power is 0. The nilpotence comes in. And when you look at j minus lambda, if you look at j minus lambda, you get those matrices that you saw in your quiz, which I don't know how. It was quite an easy problem, but a lot of you made a mistake with it because all you have to do is use the basis of the form t to the power I over I factorial, or x to the power of I over I factorial for the operator ddx. But I don't know, I thought it was totally obvious that this is the basis to use to get the correct form of the matrix. Okay. Anyways, if you use that, you can even work out the exponential of such of j minus lambda. Okay. Okay. So this can be regarded as a linear operator on VK. Okay. So it is. So it's the JIs are like that. Okay. So now, and the sum of the JIs is going to be T. Now the sets B intersection VK partition B partition B into disjoint subspaces into disjoint sets, sorry. This is a finite set B, and for each B intersection VK is a basis for VK. Okay. So, for example, yeah. By the way, what happens if you apply this to what happens if you apply this to E1, this matrix? You will get a column which has zeros, or E1, E2 up to, let's say up to here it is the size is N1, or yeah, let's say N1. What happens if I apply EI, where I is between 1 and N1, if you apply this matrix to that? So let's say J1 is 5 cross 5. If I look at E3, what will it look like? It looks like a linear combination of E1, E2, E3. If you look in a certain standard way, okay, E3 will look like actually a linear combination of E2 and E3. E2 plus lambda times E3, okay, or lambda 1 times E3. So up to E5, you will stay within the subspace V1. If V1 is generated by E1 up to E5, so the breakup, somebody asked me what is the VIs, okay? So you have changed the basis. So for the moment now, because this matrix is, you already changed the basis and you have a matrix, I'm going to worry about the standard basis, K1 through Kn. Okay. If this is of size N1 cross N1, then you look at the vector space spanned by E1, E2 up to En1, that's V1. If this is N2 cross N2, then you look at the vector space spanned by E sub N1 plus 1 all the way up to E sub N1 plus N2, that is V2, and so on and so forth. Okay, this is in Kn. K is the field, K to the power n. Now go back to your original vector space V, and then you find what, because you use the basis to come to here, and then you can talk about V1, V2, Vn over there, or Vt over there. Does that answer somebody's question? Somebody was asking me about what are the VIs. Can people hear me?
Yeah, thank you, sir.
Okay, did that make sense?
Hmm.
Okay, so look at the subspace. So for the generic one, J sub I, there are some indices. So it's of size something cross something, and it is between, and this block here is maybe between, M and N. So you look at EM all the way up to EN or something, and look at the subspace spanned by that. Call it, say, W something, and look at its pre-image under the, you went from your vector space V to Kn via standard, by a change of basis, by sending your basis vectors to standard vectors. So go back, and that will be your Vi. Okay. So it's a basis for Vk. So in other words, I'm trying to get it, this is complex, I'm trying to make it real, that is the thing. Because my original linear transformation is real. To get a Jordan canonical forms, I said, okay, I'm going to consider this linear transformation as a complex linear transformation from Cn to Cn. Then I have something, but I want to go back to reals. Okay. So this is the exercise I'm trying to do right now. Okay. I won't get exactly the lovely Jordan canonical form we have now, but I'll get something very close. Okay. So in other words, what you have is if B intersection Vk is equal to U1, I'll call it to the power k. It doesn't mean to the power k. It's just a superscript k. Where we list the elements. According to the order. The minute you talk about a matrix with respect to a basis, it's an ordered basis. Okay. So there is an order, even though I just call it a basis, obviously I mean an ordered basis because I talked about a matrix associated with it. Okay. You cannot just take a basis and say, here's a matrix associated with it. You have to give an order. You have to say, this is the first basis vector, this is the second basis vector, this is the third one, so on and so forth. So there is an ordered basis. Okay. Then Tc of Uj k is equal to Aijk Ui k, I going from 1 to Rk, where Jk is the matrix Aij k. Okay, and of course I know what that looks like. Okay, that's what Aij looks like. So Aij is either lambda or 1. Okay, so this is just matrix theory. There's nothing I'm saying, because if something looks like a this is by definition of a matrix of a linear transformation. So this is how it looks. Moreover, and this answers again Rishi Raja's earlier question, what does VK look like? Okay, it's a space generated by UI through URK. Moreover, in this way we use the fact that that we started with a real matrix. B can be chosen.
So shouldn't that one be on top of the last lambda k?
Yeah, we mentioned this is my way of writing. It is the diagonal term, lambda k. It's
Oh, sorry.
we talked about this before. Okay. Moreover, B can be so chosen that the conjugates UIK this is the conjugate. Okay. I'm trying to look at notation. So we had UI are also in B. And form an ordered basis for some VI in the decomposition above. I'm use the fact that if lambda is an eigenvalue of T, then so is lambda bar. And for that, I'm using the fact that it is a real matrix. Okay? So the characteristic polynomial has real coefficients. Therefore, if there is a non-real root, its conjugate is also there. Even if there's a real root, its conjugate is there, but then the conjugate is itself. Okay? So if you use that, and you can very easily say that if V1 through Vk form a basis for what's called a generalized eigenspace of the form Vi, then then if you look at the conjugates, that will form a basis for a similar thing. Okay, so in other words, this is if the eigenvalue of associated, okay, if the eigenvalue corresponding to Vk is real, then Vi is equal to Vk. Okay. So what I'm saying is we started with a Vk here. It has a basis. Take the conjugates of all the basis vectors, and they will also form some kind of basis for some other Vk, call it Vi. And in case the corresponding is eigenvalue is real, you can then Vk is equal to Vi. Okay? Because then you can choose your eigenvectors to be real if the eigenvalue is real. Okay? And so the conjugate would be the same thing. Okay.
Sir, what do you mean by eigenvectors to be real?
The eigenvectors are in Cn, right? so you can all, I mean, I've used a basis and I'm looking at Cn and I can break it up into real plus imaginary. Okay? That's all I'm doing. I already, in my mind, V is, though it was a finite dimensional real vector space, I'm identifying it with Rn, otherwise I will not go very far. Okay? So when I'm not using the standard basis, I'm using a different basis. I'm using a basis in Cn, but every vector in Cn can be written as a real vector plus imaginary times a complex vector. If you've done tensor products, then it's very clear what is meant by the conjugate. Okay? I don't know if in algebra you've done tensor products of modules, but if you have, then you take V tensor C. Okay? On C you have conjugation, so on V tensor C you have conjugation. You call that, so your T sub C is really a linear transformation of V tensor C. Have you done that in algebra? Has tensor products been done of modules been done in algebra?
No.
No. Okay, so if you haven't done it, the hands-on way in which I'm telling you works. Okay, choose some basis, not the B necessarily. Choose some basis of V of the real vector space V, and the way you defined TC, it's quite clear what is meant by conjugation. So let me see if I can make this a little more understandable. Okay. As an aside. Okay. You have T from V to V. Okay. You take some basis or Cn or Rn, sorry. I'll call it something, okay? Let me call it A, okay? So you can think of A as a matrix now because there's standard basis here. Via the basis. Okay, so you've chosen some basis Vn, and that goes to the standard basis E1 to En. Okay. Same. So the important thing is that these two isomorphisms are exactly the same. You're taking this isomorphism. Okay. Now take a vector V. Okay. This goes to something here. Oh yeah. So now there's some horror stuff here. So any vector here or any capital V over here. That's all I meant, okay? And I'm going to worry about this linear transformation here and work with that, okay? You can send it back to V by looking at the tensor product of V to C, but since you haven't done it, just work with that, okay? So think of V as Rn and the new V as, and look at Cn, look at a vector there and break it up, okay? So where are we? Otherwise, Vi is not equal to Vk.
Sir, what is I again?
Not a, what VL, let me say. For some VL. So what was VL? You had a VK, you fixed a VK to begin with. You took a basis, took it the conjugate vectors. That gives you, according to the way the basis is chosen, some other V, that is VL. Okay? The one of the V's which is generated by the conjugates of the basis of what did we begin with? VI, or was it V? Yeah, of VK. You started with a VK, look at the conjugate basis, call it VL. Okay. In case the eigenvalue corresponding to VK is real, then VL is equal to VK. If it's not real, then they're different. Okay. So now let V be one of the VK, and without loss of generality. Assume V is equal to V1. Okay. So I started with a VK, but I'm going to now let J be the corresponding Jordan block. So J1, if you wish. Okay. Assume the eigenvalue corresponding to J, the eigenvalue lambda corresponding to J is not real. Okay. So lambda is not real. Okay. So let B intersection V. I'm just repeating what I just did, but with less notation so that it's clearer. Let B intersection be this. The ordering of the subscripts respecting the order in B. Okay. From the form of J, we see the following, that TC U1 is equal to lambda U1. Then after that, TC of UI is equal to UI minus 1 plus lambda UI. Okay, this is for I from 2 to, what was it? What did I have here? R, okay. R, yeah. This is R, this R. Okay. Did I have RK before? Yeah, I must have had RK before. Yeah, so I've just made K equal to 1 and dropped the K. Okay. Since lambda does not belong to R, okay, so from what we said above, if W bar if W I is equal to ui bar I going from 1 through r. Okay, then is an ordered basis. For some vi. So you know what, in my tech notes I will just take rn rather than v. Okay, so maybe when I take it up I'll just use rn, and then that will make this easier, because the confusion about what is the conjugate of an element, you need a tensor product of. But if I use v equal to rn, then when I look at C, and conjugation has no problem at all. So that's what I will be doing when I write the tech notes, and that will answer some of the questions that were asked. I think Naman asked a question, a reasonable one. So that will be the way we will solve this issue. Okay. So my T will be endomorphism, a linear endomorphism of Rn to begin with when I make the tech notes. I've already written too much here to change it here. Okay. Okay. Since lambda is not equal to R, since lambda does not belong to R, Vi is not equal to V. This was not V, what was it? V is the eigenspace, okay, yeah. So Vi is not equal to V. So we may as well assume V for some VL, sorry. I think the way we wrote it was some VL. L is equal to 2. So W equal to V2. So without loss of generality, we assume that V is V1, and we'll assume W is V2. Okay. So from what we have seen, TC of W1 bar or W1 is equal to lambda bar W1, because the conjugate so note, if you put these two n vectors, U1 through UR, W1 through WR, the two R vectors. Okay, and this is a basis. Is a basis for V tensor W contained in Cn. This half is the basis for this, and this half is the basis for that. Okay. So for the direct sum, it will be a basis for between both of them. Now do the following. This for J belonging to 1 through R, let Cj equal half Uj plus I bj. I mean, I can half Uj plus Wj, sorry. And dj equal to half Uj minus Wj. Then it's easy to see that Uj, this is the decomposition of Uj into its real and imaginary parts. And moreover, Cj, Dj belong to Rn, whereas Uj, Wj, as far as we know, they belong to Cn. They may or may not belong to Rn. But we are sure that these two. Of course, they belong to Cn rather than Rn because eigenvalue is complex. So it follows that the span, the complex span of U1 through UR, W1 through WR is the same as the complex span of C1 through CR, D1 through DR. So C and D are real vectors, but now if you take complex linear combinations of them, the linear combination may or may not be real. Okay, but the complex linear from these formulas here, it's quite clear that that the spans are the same. Okay, I've written each as a linear combination of the others. So from these formulas, it's clear that the complex span is the same. Notice the i's that are coming in here. So obviously I have to talk about complex spans, okay? Okay. In particular, C1 through CR, D1 through DR is a basis of V direct sum W. So let me remind you that we broke up, Cn into V1 direct sum V2 direct sum Vt, and that was long ago. Now currently we are in a situation where V1 is V and it has a non-real eigenvector. Take its conjugate and we decide to call it V2, and that's W. Okay, it has two names, V2 and W. Okay, so if lambda is equal to A plus IB, an easy computation shows that TCJ is equal to ACJ minus B, minus BDJ, and CJ minus 1 plus ACJ minus BDJ for if J is equal to 1, and this is if J is between 2 and R. And similarly, if you look at, so this is just using these formulas over here. If you use these formulas, and you know how T behaves on each one of these, you know how T behaves, you know how T behaves here, you know how T behaves here, you know how T behaves here, here and here. So you can work out how T behaves here. It turns out this is how it works. Okay, and T of DJ, this is CJ, is something similar. If J equals 1 and is equal to DJ minus 1 plus BCJ plus ADJ if J is between 2 and R. Okay. These are totally trivial to see. So if we modify our basis or order, or ordered basis, so that the first two R members are C1, D1, C2, D2, CR, DR. Okay. In the beginning, we had this order. Actually, in the beginning, we had this order. Then we had this order with the U's and W's being replaced by real vectors C and D. First the C's, then the D's. Now I'm alternating them. And do this for every pair of conjugate eigenvalues, which are not real. Okay. Then the matrix of T with respect to this basis is such that the blocks corresponding to segments like, for this one, that means the vector space generated by these have the form. I'll call it J tilde, lambda, lambda bar, if you wish. It'll look different. It'll look like M, I2, M, I2. Keep me honest because I tend to, this is in the diagonal and this is above the diagonal. Sometimes I write the way my handwriting goes, it doesn't go that way. Okay. Where I2 is, of course, 1, 0, 0, 1, and M is of the form A, B minus B, A. Okay. So now you get something of a different kind. So now your Jordan blocks look a little different. They don't look neat. They still look like a canonical form where you think of this identity matrix as 1, and you think of this as some kind of generalized eigenvalue, except it's a 2 cross 2 matrix. So these are 2 cross 2 and 2 cross 2 matrices. Okay. Okay. These commute. So it's quite easy to work out. So we'll see this. So it turns out you already know the exponential from your quiz. Okay. It has a certain form. It's quite easy to see. This is part of your homework. E to the power Tm. I'll tell you what it is. I actually write e to the power m, but you'll have to work it out. Will be e to the power a times cos b minus sine b cos b, something like this. Okay. And so e to the power tm will also look like e to the power ta times cosine tb and stuff like that, or whatever it should be. And then you can work out many things. Okay, so Actually, I think that's just wrong. One of the two. By the way, this is really a disguised form of A plus IB. Matrices of this form, they form a subring of 2 cross 2 matrices. In fact, they are field. In fact, the field is the complex numbers. We have this method, and the operator norm agrees with the usual norm on A plus IB. You can check that very easily. So not only is it algebraically isomorphic to the complex numbers, it is on the nose isometrically isomorphic to the complex numbers. So stuff of this form. So it's not at all a surprise that that you get this. Okay, and you get it by just taking the power series. So that's how the exponentials will look. But exponentials behave well with respect to block matrices. We'll do that next time. So in the end, when you take all these, and also with respect to conjugation. So suppose you conjugate a matrix gamma A, gamma inverse, the exponential of this is a conjugate of A with respect to gamma. And that's also totally trivial to see, because I'll say this and I'll remove it. So note, if B is gamma A, gamma inverse, then sigma I going from 0 to m of b to the power I factorial is gamma I go. Okay, by letting m go to infinity and using the fact that matrix multiplications respect limits. Okay, we proved all those things. So you end up with something like this. So you actually end up with whatever we want, and we'll do more of this next lecture. Okay. So what I'm going to suggest is I'm not going to ask you the proof ever of the Jordan canonical form. It is not part of this course. I gave it to you so that you have something to chew on. I know it doesn't make too much sense because you don't even know the real proof of the real part, and therefore, sorry, of the complex part over an algebraically closed field. But take that statement as a given. Remember that if you rearrange the basis that you get from there over the complex numbers, you can make it, you can get a real basis in which the canonical form looks a certain way, namely this way. It looks, instead of Jordan blocks of the real form, the Jordan blocks of the, sorry, of the complex form, the real Jordan blocks look like that for eigenvalues which are not real. For eigenvalues which are real, the new Jordan forms look like the old Jordan forms. For the eigenvalues which are not real, you can combine two different Jordan blocks, the one corresponding to lambda and one corresponding to lambda bar, in such a way that the new Jordan block, and change the basis just a little, so that the new Jordan block is a real one, and it looks like this. So now you are in real parts, and the whole part, the difficulty is working out the exponentials of this. And so this part is the part of your homework due on Friday to work out the exponential of J tilde. You do that. And so I'm going to assume that, and I'm going to do a little more about exponential next time. And that will, and draw out the consequences, what I've been saying verbally. I'll say it in a more formal written way. So don't worry too much about the proof of the real Jordan form. But to have a handle on it, you should understand the basic idea of the real Jordan form. And I will say this again just for the next 1 minute, what the basic idea for the real Jordan form is. Take the complex Jordan form. Okay, it looks in a certain way. Okay? It looks something like this. Okay? Now, on this complex Jordan form, so I'm trying to look at the screen on, if I look down, I'm trying to look at it in my laptop. Okay. So look at the complex Jordan form J1, J2, Jt. Let's say the first two, three, one of them correspond to eigenvalues which are not real. Let's say J1 corresponds to an eigenvalue which is not real. Say lambda. Then lambda bar also has a Jordan block. And in fact, you can choose your basis in a clever way so that that Jordan block's basis is the conjugate of this Jordan block. So let's say J2 is the corresponding Jordan block for lambda bar. So what we are saying is that we can somehow cleverly combine this J1 and J2 in such a way, so change the basis. Now the bases are in Cn, change the basis so that they become basis in our, vectors of some things in of the combined space generated by these two, and they're from R. And rewrite this matrix. What you will get instead of this will be something larger. Instead of this part, you'll end up with something which looks like m times I2 times m. Okay, so J1 and J2 will have the same size because they correspond to the conjugate eigenvalues. So this together, this will look like this. Well, I should not say it'll look like this. It'll look like okay. So this will be 2R cross 2R, and this will also be 2R cross 2R. But the difference is this will be complex here, whereas this will be real. Okay, that's the difference. And the exponentials of these such things is what your homework is about. So in case you're wondering why we are doing what we are doing, that's for that reason. If you're looking at your homework and seeing why did this problem in linear algebra come, it is for this reason. There's a bit of analysis there because you have to look at the exponentials. Okay, is that clear? So I'm going to end the meeting now. Adityan, I tried to ask about the dogs. They didn't know. I didn't ask the security guards. I asked somebody else. So today I'll be going to CMI soon, and I will try to find out. Is that okay?
Thank you, sir.
Okay.
Sir,
Yes.
sir, in the last question in homework 4,
Yes.
so I have proved the required inequality for the case where t is greater than t naught.
Yes.
So like I was wondering if you can give some hint as to like how we handle the other case, because a straight
How
time
about you?
reversal does not seem to work.
What does not seem to work?
Like doing a kind of time reversal. Like,
Why doesn't it work?
huh?
Why wouldn't time reversal work?
As in, like according to the notation of the problem 6, if we take like the whatever we take u and v to be, then like the other inequality will hold. As in, like it would be the case that u dot minus v dot greater than equal to u minus.
No. Suppose the final inequality is true for t greater than equal to t naught.
Yes.
That fundamental estimate.
Yes.
I see no reason why it would not be true for t less than t naught. Why?
As in, like I'm not claiming that it's not true, but like I'm just asking.
No, I'm not. I'm saying why that just from here it cannot be reduced. You are stuck with u and v and all. I'm saying use UV or whatever you wish to get at that inequality at the end. Okay, that fundamental estimate of the difference of the two approximate solutions in terms of delta and epsilon. Okay, it's for t greater than or equal to t naught.
Yes. Mm.
So I don't see why it won't work. From there you cannot deduce it for t less than t naught. You're trying to make the proof work. I'm trying to make the conclusion work. Take the conclusion and make it work.
Sir, it's almost 10:50, so can we leave now?
Yeah, but those who wish to leave, leave. If somebody wants to ask a question, they can leave. All of
Yes.
us. Yeah.
So I
Yes,
had
sir.
a same doubt about this thing. So like, can you again explain what you said to Rishiraj?
So what I said to Rishiraj was, if you got your inequality for t greater than or equal to t naught, the last inequality, I'm not talking about the proof. Okay. So then you should be able to use time reversal to get the same inequality for t less than t naught. Okay, that was the point I was trying to make, and
Yes. So sir, in the quiz, you told a basis for which you told the choice of basis to be x square over 1 x square over 2 factorial and x cube over 3 factorial. So
yes,
sir, what I have done is I constructed my matrix with respect to v comma w, where v was the standard basis and w was 1 x square over 2 x cube over 3 and so on. So the matrix looks still the same.
no, it can't be the matrix cannot look the same. The matrix will not look like 0, 1 if you just look at it carefully. If you differentiate, what happens?
So if I differentiate the differentiation of x square over 2 is this x only, and x cube over 3 it's 2x it's x square.
But you wanted x squared over 2. I mean, what I'm saying is okay. So you're saying that you're able to solve the problem with that?
Yes.
Nobody's going to cut marks if your solution is correct.
Sorry, sir.
We're not going to cut marks if your solution is correct.
Okay, sir.
What you're saying is that there is another way of doing it. I doubt it somehow, but I will look at your solution. Okay.
Okay, sir. So I took the matrix with respect to v comma w, like on the LHS for v comma w, where v was the standard basis and w was the basis which I told you.
So for the polynomial ring, you took a certain basis, and v comma, then that won't help, because when you take higher powers, things become different. If you're going to talk about a to the power n, you should use the same basis at both ends. Otherwise, the matrix, suppose you look at a squared, then now you take the new basis and yet another new basis, okay, with respect to something else. That becomes much more complicated. It's not, you no longer have matrix multiplication if you change the composition of those vectors, will be more complicated then of those linear transformations. Okay, unless you have, so suppose you have a vector space V and a linear transformation from V to V, call it T. If you choose a basis for the domain and a basis for the range, of course you get a matrix. But T squared will not be a simple question of multiplying this matrix with itself. Okay, that becomes far more complicated. Okay.
Sir. Yes. So for that question which I mentioned, number 8.
Yes.
So for the original set, this happens is what happens is that we get u dot less than equal to f of u. F,
That is
f,
for, yes.
yeah, f of u v dot equals to f of v. And,
Yes.
yeah, and like the rest works out as in problem 6. But
Yes.
for the time reversed case, like I will again be calling them u and v. So
Why
like,
are we, I said again and again, forget about u and v. Once you've got this inequality, once you have this inequality, forget about u and v. Now see if you can get the other inequality using this inequality, using time reversal. Forget about u and v now. Just look at the final inequality. Okay? And see what you get. Okay, so change your phi and psi. Okay.
yeah, sir, but like there is no guarantee that so like I was thinking that like maybe that kind of
The
argument.
time reversal, it'll still be an approximate solution of the new epsilon approximate solution of the new differential equation. If you change phi to some psi and v to some minus v, and psi of t is phi of minus t, and instead of v you have minus v, okay? If you look at that, it's still an approximate solution. The new psi is an approximate solution of the new v. Now look at the forward time for that and use the inequality you already have. Okay, not phi and psi. Call it something else. Okay, you have phi and psi already as approximate solutions. Call them something else for the time reversal ones. For the change your differential equation from x dot equal to vtx to y dot equals minus vty. Okay, on minus of I. Okay, or something like that. Or whatever, if not minus, assume t0 is 0. Now change your phi and change your psi across as instead of phi, the new phi is phi tilde, which is phi of minus t, a psi tilde, which is psi of minus t, or something symmetric around t naught if your t naught is not 0. And apply
Specifically
the
2t naught minus.
huh?
Specifically 2t naught minus I.
Specifically
2t naught minus I. As in like 2t naught minus whatever is.
whatever you do. Now you already proved the forward part, apply it to this one. It doesn't only apply to that phi and psi, it applies to all phi and psi approximate solutions and all v. So now you change your v, phi and psi and you apply this. I don't see where the problem is. And you can check that it's still enough. These are still approximate solutions of the correct approximations.
Okay, thank you.
Right? Did that make sense, Rishiraj?
Yes, yes. Actually, like
okay. So I've
I
given
did
you a
not
solution.
change the did not change the like v to minus v. Probably that's why I was having a problem.
I mean, how do you get a time reversal unless you do something like that? Right? I think
Yeah,
so.
thank you, sir.
Okay. Okay. Anyway, okay, so people can leave, as I said. This is not, I'm just answering random questions of people. Okay, if there's nothing else,